Hello TaleForges, I have something special for you. Lately, I have been playing around with compute shaders in my spare time, like in the last showcase video, and I would like to share my knowledge with you. That's why I want to show you how to implement the FallingSandParticles shader with ECS code. So let's dive in. As you can see, I switched to PC platform and set Full HD resolution for this tutorial. First of all, let's create directory FallingSandParticles and ECS scripts. DrawComponentData, DrawAuthoring, DrawSystem, which will control pixels, DrawInputSystem, which will control input for the drawing. Also, we need to prepare enum DrawInputMode. Then, after all the scripts are created, let's prepare the initial texture. I just copy and paste from my resources. It's all green color because green pixel is considered as obstacle. Red pixel will be sand particle, and black pixel will be empty space. In the inspector, let's select texture type to sprite. Also, uncheck alpha is transparent checkbox. I want to have black background. Last thing to do, let's create a new compute shader. Name it FallingSandParticles. Great, so now let's prepare a new scene, FallingSandParticles scene, in which we have to leave the main camera object, but we can freely delete the directional light. Let's modify parameters of the camera, position Z to -1. Also select background type to solid color and projection to orthographic. Let's adjust orthographic size to 1. Okay, now create new ECS subscene, FallingSandParticles ECS. Here, let's add a quote. Create a new material, FallingSandParticles, and set it to URP unlit. This will be our display for the render texture created via code. Drag and drop FallingSandParticles material. So set scale on the quote. We want to remove a mesh collider from this object and use box collider to detect the raycast via ECS and change box collider Z size to half. Also create a new object, draw, and attach a DrawAuthoring component to it. Here we need to select references and parameters later. I want to use new input system, so let's create InputActions and name it DrawInputControls. Select the asset and check Generate C# class. Then apply. Wait for the compilation process to finish. Then, inside the asset, let's create a new draw map and prepare 4 actions. Pointer position with action type value and control type vector 2. Let's choose the path to the position pointer. Space action with the path space keyboard. Left mouse button with path left button mouse. And the last one, right mouse button with path right button mouse. Remember to save the asset so our changes are propagated to the generated C# class. In the DrawComponentData, we want to store references and parameters of the draw system, so it will be managed type. Let's implement IComponentData interface, then create 6 parameters: ComputeShader, texture, material, draw width, obstacle width to control brush size, and eraser width. Okay, let's go to the DrawAuthoring class and create 6 serialized fields for ComputeShader, texture, material, draw width, obstacle width, and eraser width. And of course, getters. I forgot to add namespace in both scripts, so let's correct this. Then create the drawBaker class, and inside the bake method, write getEntity with transferUsageFlag.none. Let's add component object and pass all parameters to the new DrawComponentData. That's it. It's time to create our first ComputeShader in the TaleForge history. We can remove all comments. I will explain everything in a moment. At the top of the file, you can see Pragma kernel CS main. Each kernel tells which function to compile. It is possible to have many kernels, but we only need to add one. So let's rename kernel and function to the FallingSandParticles. We can remove any code from the function and leave the result variable. It will come in handy later. We can leave num threads as default, so 8 in one dimension and 8 in the second dimension. In other words, 8 multiplied by 8 equals 64 threads. Okay, let's start with creating all needed variables: float2 pointer position, float draw width, float obstacle width, float eraser width, float time, int texture width, int texture height, and int draw mode. Also, let's rename result to result with small letter. Now let's implement FallingSandParticles function. Noteworthy that these compute shaders calculate every pixel of the texture when called. We will call ComputeShader via DrawSystem. We need to get the pixel position, or in other words, pixel ID. So let's create local variable int2 new pixel ID. xid is equal to pointer position.x multiplied by texture width. yid is equal to pointer position y multiplied by texture height. Now we can write const float for new pixel equal to result new pixel ID. It is basically value of the pixel in the color. Const means that this value will not be modified in the future. So something like read only in the C#. We need to get current pixel ID and value. Const int2 pixel ID equals id.xy and float for pixel equal result pixel ID. Based on this data, we can perform all the necessary operations, of course, transforming the color of the pixel or its position ID accordingly. It's time to check draw mode. If draw mode equals 0, call DrawParticles with parameters pixel ID, new pixel ID, and new pixel. Else if draw mode equals 1, call DrawAuthorings with parameters pixel ID, new pixel ID. Else if draw mode equals 2, erase obstacles, pixel ID, pixel, new pixel ID. We will implement these methods in a moment, but now let's check if pixel.x is equal to 1 and x equals red color value, so our particle. If so, execute FallingSand logic with two parameters, pixel ID and pixel. Okay, let's start implementing our functions. One important thing, when we use one function in another, the use function must be above the function we are calling from. It is something similar to programming in the old good C language. Void DrawParticles const int2 pixel ID, const int2 new pixel ID, const float for new pixel. And inside this function, we can write const float this equal distance float2 pixel ID, float2 new pixel ID. You might ask why we need a distance. I want to draw particles in some radius, not single pixel. That's why I check distance of every pixel, and if distance is bigger than draw width, simply return. But otherwise, if this pixel is empty, I can assign red color to the result pixel ID element. Of course, let's implement bool isEmptyPixel function with parameter const float for pixel. This function is really simple. Just return true if conditions are satisfied. Pixel.x and pixel.y equal to 0. We can also create the function bool isOfSequ const float for pixel with return pixel y equals 1 because we will need this function soon. Okay, now it's time to implement DrawOfSequs. Create parameters const int2 pixel ID, const int2 new pixel ID. Again, we can check distance, and if distance value is smaller than offset width, we spawn offset, so result is equal to green color. Next, let's create erase obstacles, this time with parameters const int2 pixel ID, float for pixel, and const int2 new pixel ID. This function also checks if distance is greater than eraser width. If so, return. Otherwise, if it's obstacle pixel, set pixel to black. Okay, it's time to implement void function. Execute FallingSand logic. int2 pixel ID, const float for pixel. First of all, we want to set the direction to int2 0 minus 1 because the particles need to fall down. Result pixel ID is equal to pixel ID plus direction. In turn, result pixel is set to result at result pixel ID index. Then we want to check if result pixel, so pixel below current pixel, is occupied by particle or obstacle. If so, we set the direction.x to pseudo-random number -1 or 1. Unfortunately, we don't have functions to randomize numbers, so it's good time to introduce hash functions, which lets you generate pseudo-random values. In this field, I found great page, shadertoy.com, where are a lot of useful hash functions ready to go. Okay, so let's search for random and select hash without sign implementation. Then go to the common tab, search for the hash 1, 2, and copy-paste to our code. Now let's modify vec2p to const float to p2 in the parameters. Change all vec2 and vec3 to the float2 and float3. Don't forget to modify frag to the frag. Let's add summary. In the brief, we can add source to the hash function. In the param section, p2, float2, parameter. And in the return section, pseudo-random number. Great, let's back to the direction x, assign sign, hash 1, 2, float2, pixel ID, plus time, -half, so we get range from -half to half. Then assign result pixel ID and result pixel in the same way as before. If result pixel is empty, we can write set pixel and pass 3 parameters, pixel ID, pixel, and result pixel ID. Then return. So let's implement the setResult function. It is a void function in which we set result pixel to pixel value, in our case red color, and reset previous pixel location to the color black. Okay, back to the execute function. Let's write direction.x equal minus direction.x because I want to check opposite side. Assign pixel ID plus direction to the result pixel ID and result at the result pixel ID index to the result pixel. Again, we check if result pixel is empty, and if so, set result. Of course, pass necessary parameters. This way, we check both sides of the slope. That's it for the ComputeShader. Before we move on, I would like to invite you to support us on Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in the description. This system is responsible for communication between ECS input system and ComputeShader. First of all, let's add partial keyword and inherit from system base. Remember to implement missing method. Next, add update in group type of simulation system group attribute, and then we need to add private static read only properties for ComputeShader. So let's create draw mode ID, pointer position ID, time ID, base map ID, result ID, draw width ID, obstacle width ID, eraser width ID, texture width ID, and texture height ID. We can also create two needed variables, private vector to in, thread groups, vector to in 0. This parameter is necessary to dispatch execute ComputeShader, and private int kernel. First of all, create method which will execute shader logic. So let's write public void execute ComputeShader with three parameters: ComputeShader, pointer position, and DrawInputMode. And pass parameters to shader via setIn DrawModeID. We need to modify DrawInputMode, so let's open DrawInputMode and change class to enum. We need four states: none, which is basically default mode in the DrawInputSystem logic, DrawParticles, DrawObstacles, and EraseObstacles, which allows us to react to the pointer position and execute ComputeShader depending on the state. Okay, let's back to DrawSystem and fix variable name. Then set vector pointer position ID, set float time ID, and at the end call our execute ComputeShader.dispatch kernel threadgroups.x threadgroups.y and 1, because we don't use that dimension. Let's implement onCreate method with require for update DrawComponentData. Then create onStartRunning, where we assign system API.manage_API.getSingleton DrawComponentData to the DrawComponentData. Next, cache DrawComponentData.texture to the initial texture local variable. Let's create size variable and assign it to the new vector to in with texture width and height. Also cache ComputeShader from DrawComponentData. Finally, find kernel by name, FallingSandParticles. Now we need to create a render texture for ComputeShader to operate on. So let's write var render texture create render texture size. Add private render texture create render texture vector to inSize method, and inside it var render texture equal new render texture size x, size y 0, set wrap mode to clamp, filter mode to point, and enable random write to true. Call renderTexture.create and return render texture. Now, important thing to do, we need to call graphics.bleed initial texture render texture, which use a shader to copy the pixel data from a texture into a render texture. It's time to set texture on the material, pass base map ID, and render texture. We need to do the same thing in the ComputeShader, but with the kernel, result ID, and render texture parameters. Then pass all the necessary parameters, it as draw width, obstacle width, eraser width, texture height to the ComputeShader, so that it is correctly configured. Last thing to do, we need to get kernel thread group sizes. These parameters are necessary to dispatch shader. Let's divide texture size by thread group size. Okay, it's time to handle input. First of all, add partial keyword and inherit from the system base. Of course, implement missing methods. Next, add attribute to the class, update in group type of presentation system group. In this class, we need to create DrawMapActions so we can subscribe to the events. So let's add private DrawInputControls DrawMapActions variable. We also need to call the executeComputeShader method from DrawSystem. What's more, it is necessary to make calculations in relation to the camera, especially the screen point to ray and world to viewport point functions. So we'll need to prepare variables for camera and collision filter. Okay, it's time to create new method, protected override void onCreate, in which we write DrawInputControls, enable input, and cache DrawMapActions. Add required for update DrawComponentData and physics word singleton. And now, let's create onStartRunning method. Here, get existing system manage DrawSystem, cache camera.main, and prepare collision filter, which will allow to interact with any colliders. Then, in the onUpdate method, let's get singleton, DrawComponentData, and cache collision word from the physics word singleton. Let's create a local variable, DrawInputMode, equal to none. If DrawMapActions left mouse button is pressed, assign DrawInputMode, DrawParticles to the DrawInputMode. As if DrawMapActions right mouse button is pressed, assign DrawInputMode, DrawObstacles to the DrawInputMode. As if DrawMapActions.space is pressed, assign DrawInputMode erase obstacles to the DrawInputMode. Then we need to get pointer position in relation to the texture coordinates. So let's create private vector2 get pointer position collision word method, and inside it read pointer position value vector2 from pointer position action. Next, ray equal to camera screen point to ray pointer position. We want to detect the ECS collision, so we can't use physics raycast, and instead we need to prepare raycast input variable. Start is equal to the ray origin, and is equal to the ray.origin plus ray.direction, and filter is the collision filter. Now, if negate collision word.cast ray input out var hit, so we don't detect collision, let's return vector2.0. Otherwise, we will return camera.word to viewport point hit position. As I said before, I will use viewport calculation to get the mouse position in relation to the texture UV positions, basically simplifying the process to the needs of the tutorial. Last thing to do, let's call DrawSystem.executeComputeShader and pass parameters. DrawComponentData.ComputeShader, pointer position, DrawInputMode. Great, we handled the input controls. Okay, so let's go back to Unity, wait for the compilation process to finish, then select Draw Component in the ECS subscene and pass ComputeShader, Texture, and Material References. Based on my texture size and experiments, I decided to set Draw Width to 6, Obstacle Width to 10, and Eraser Width to 20. Okay, so let's test everything out, hit play, and as you can see, something is not right. There is a problem with the ComputeShader because our sand is not falling. Aha! Here's a problem with pixel ID, so let's change it to pixel. Okay, let's try again. Hit play and let's have some fun with our newly created ComputeShader. Fantastic! Well done! Thank you for your time. I'm glad you are with us and our community is growing. See you soon in the next video.